Right, good afternoon and welcome to this week's Iowa Learning Farms Conservation Webinar Series. I'm Matt Helmers at Iowa State University and have the great pleasure of getting to moderate the webinar again today. And my pleasure to introduce a colleague of mine, Dr. Marshall McDaniel, that is an associate professor in the Department of Agronomy here at Iowa State University. He's going to be talking about directly linking soil management and the eutrophication of Iowa streams. As always, if you have questions, please type those in the chat box and we will get them to Marshall at the end of his talk. And with that, I will turn it over to Marshall. The virtual floor is all yours.
Sure, thanks, Matt, and thank you for the invite to come present to all the Iowa Learning Farm group here. Here's just a couple other voluntary demographic survey. We
can go back to that at the end of the talk, Marshall. So
okay, good. Those are on the
you just
slide.
jump in there and we'll do those at the end.
Okay, great. Sounds good.
That one.
We'll come back to that one. All right, great. Again, good afternoon, everyone. Thanks for inviting me, and I'm glad to be here. I'm going to be talking about streams like this, which is sometimes we refer to these as agriculture ditches. They're kind of the first line of defense or line of impact after our tile drain. I was really happy and also want to give a shout out to the Iowa Nutrient Research Center, which funded this research now. Oh, I think it was 4 or 5 years ago, we got this grant. And it's one of the first of its kind experiments where we take water from under different soil management practices and mix it with streams and measure the eutrophication in a lab. So under kind of potential or ideal settings. But I'll explain that a little bit more as we progress here. And I'll cover some backgrounds and objectives of the study, a little bit on the experiment design, the findings, and then some conclusions, some take-home messages. If I do not get to your question, you can email me at marsh@iastate.edu, and you can find all the cool research that folks in my lab do. I try to just stay out of their way at soil_plant_IXNS, which is short for interactions. And the person I need to give credit to for doing all the work, including helping with the proposal writing to the INRC, is Merganka Day. He's now an assistant professor of biology at Minnesota State University. And he, like me, also had a background of water quality work and experience at his graduate school. So we were both kind of working on soils for several years, in my case, probably decades or more. And him being a few years out working in soils, but coming back to streams. Okay, so one of the background things I want to bring up is that there's a long history of research on algae growth, which is kind of the first stage of eutrophication, right? Algae grows, then that algae dies, gets consumed by heterotrophic organisms that use oxygen, and then that becomes the problem, right? Not the algae growth itself, but when that algae biomass starts to decompose. And going back to the 1970s, even prior to that, this is a picture from the 1970s from an experimental lake in Ontario, Canada, where they could section off or wall off a part of the lake, and then they can add nutrients. And you could see half of this picture, the water is much greener than the other half. And that's probably the side, I didn't get this from the picture, there wasn't a caption to it, but I presume that's the side that they added nitrogen or more likely phosphorus in that study. There's also been some research in algae growth in streams from Iowa State. These two gentlemen likely retired, or if there was a student left Iowa State before I arrived, but in 1988, they published this paper in Hydrobiologia where they used gel that was implanted in soil terracotta pots, and then they placed them on a board. This is actually a diagram from the study. And then each of those, the gel inside those terracotta pots was infused with nutrients, either nitrogen or phosphorus or both. And they looked at the algae growth on those terracotta pots as a indicator of eutrophication or limitation of those nutrients when that was placed in a stream in Iowa. More recently, they've folks like this Dodds and Smith paper have looked at total phosphorus and total nitrogen, so both nutrients, and how they might co-limit chlorophyll production. So a lot of research has been done, but we still, there's still a lot we don't understand about nitrogen and phosphorus limitation and that direct connection to eutrophication in streams and lakes, I would imagine too, although I'm not in that research realm as much. So we do have a pretty good understanding of management effects on nutrient loss, right? Work by Matt Helmers here, our host, and others who have done these individually tile drained experiments. And there's other types of ways of measuring nutrient loss under different management practices. But we now understand pretty well that which management practices reduce nutrient costs. This is part of the Iowa nutrient reduction strategy. However, where we lack knowledge is this connection between the nutrient loss in a tile drain, like this one shown in here in Illinois. This is one of the streams I worked on when I was a master's student. And then what happens within the stream eutrophication. And this is showing a kind of a sandy sediment gravel base of that ag ditch. And you could see the striation in that stream. That's all paraphytic algae. So kind of growing on that sand, these long stringy strands of algae growth. And some work that he's now retired, but my master's advisor at the University of Illinois at the time studied a lot of these factors on what did cause stream eutrophication, whether it was the stream size or other characteristics dictated by flow. The canopy cover seemed to be a big important predictor. And a lot of these ag ditches don't have trees on it, like the one pictured here in the center. And that makes eutrophication all the more easy to happen if you have a light source into that stream. This is what I did my master's on, was the benthic sediment or the substrate as well. That all affects eutrophication dynamics, prior nutrient load, and a host of other factors that I'm not going to go into. But I am going to focus on the stream size and flow because that pertains to the study I'm going to talk to you about today, and also prior nutrient load. And this is one that hasn't gotten a lot of attention. Is actually very difficult to tease apart and study, because it requires, studying a stream for a long time and then implementing a management practices in that watershed, and then measuring the impact for many years afterwards too. So our experiment kind of shortcuts this or reroutes this and allows us to do this with a short-term incubation. I'll explain those details in a moment. But our three major questions, kind of in order of importance, were how do management practices directly impact eutrophication potential in a stream? And I use that word potential on purpose because this is in an ideal situation. So temperature is ideal. We have light conditions that are ideal. So this is not necessarily reflect what is happening in situ or in the stream, but can happen under ideal conditions, right? The other one that our secondary question was, does the prior stream condition or that what I mentioned, that previous nutrient load, matter? So are more pristine streams that have lower background nutrient concentrations and likely less algae growth and eutrophication, are those more sensitive to new inputs in tile water? And then the final question that's kind of the least important, but we were still interested in and part of the experiment, is does the mixing volume or the tile water to stream water regulate this eutrophication potential as well? And what I mean by that is that, you could have a tile flow that's very heavy, but an ag ditch that's dry or just has a small trickle. And so the proportion of tile water to that stream water is really high compared to a larger stream or ag ditch like this picture up in the upper right. And there's a trickle of tile water coming out as in the picture, and it's a lower mixing volume. So those are the three things we studied in this potential experiment. The objective was to compare the impact of tile water under conservation practices versus a business as usual management So that's corn, soybeans with no cover crop. On stream water eutrophication, so directly measuring eutrophication. Additionally, we wanted to know, does the prior history of nutrients matter and the mixing volume? And we simulate this a change, we're simulating a change in land use, right? So a stream that maybe prior didn't have a lot of nutrient inputs prior, but then because of land use change now is receiving nutrients. So we're looking at this kind of historical importance of nutrient loads, and then also flow conditions, and these can be considered sub-factors. And our hypotheses were tile water from conservation management practices, including rye cover crop and a restored prairie, will decrease eutrophication compared to the business as usual, which is conventional corn, soybeans. Our second hypothesis related to the prior nutrient inputs was streams with a prior history of excess, without a prior history of excess nutrients. So we call these low impacted streams, less than 1 milligram per liter of nitrogen, will be more sensitive to eutrophication than streams regularly showing high nutrient concentrations. Our medium and high impacted streams that are above 5 milligrams per liter. And then we hypothesized that greater mixing volumes with the tile water will further exacerbate eutrophication. Okay, so here's a little bit of how we did it. We collected water from the Cobb's experiment, the comparison of biofuel systems, just about a 10, 15-minute drive from Ames. And we collected water we did this actually at 2 times. I'm just going to show one time point, but the results were almost identical. So we collected water in the fall when tile water flow is high, and in the early spring. And we collected it under a leaky system. This would be our corn soybean rotation, as greater amounts of nutrients we would expect, and we did find. I'll show you the analyses. And then under the restored prairie that had very little nitrogen and phosphorus flowing out the tile line. Then we took those sources, the corn soybeans, corn soybean with cereal rye and restored prairie, and mixed them with 3 stream waters: a low impacted stream, medium impacted, high impacted, meaning that there was already a history of pre-existing nitrogen, phosphorus, likely more eutrophied too. And then we mix those in 3 mixing ratios. So C is our kind of third factor at 5%, 10%, and 25%, or a 1-to-4 ratio. A little bit about those streams. And so we were able to get the history through the Iowa Water Quality Information System, the Iowa USGS database and website. We looked up several streams, and we kind of we're looking at this historical data. So we collected samples in 2019 or maybe end of 2018. And we wanted to know the past 3 years and look at that record. And this is our low impacted stream, Catfish Creek, from Dubuque, Iowa, shown here in the star. And then the nitrate and nitrite concentrations, you can see, are mostly below 2. Average is probably about 1 from April to September across all 3 of these years. Our medium impacted stream was Bear Creek, nearby here. Here in Story City, near Story City, Iowa, in Story County was what I was trying to say. And here the average concentration over the 3-year historical data was about 5, maybe somewhere between 5 and 10. There's some points where this stream does in May and June of 2018 and 2017, it's above 10. But this is what we considered our medium impacted stream. And then a high impacted stream was Tipton Creek up near Hubbard, Iowa. And here you can see almost all through April to September, except for 2017, it was a little bit lower, maybe closer below 5, but exceeding 10, if not close to 20 parts per million during many months of the year, especially in April through July. So here, when we collected the water, so those were prior data from the USGS, but when we collected, this is what we found Dissolved oxygen was greater in the low impacted stream as we expected. There's more or less more nutrients as you move from kind of the low impacted to high impacted, whether that's dissolved phosphorus, total nitrogen, or nitrate, all kind of increases with impact, just as we expected. So this was just good to see that, yes, we collected streams that differ in their nutrient content at the time we collected the samples. So how about the tile water under Cobb's management? So we also found that what we expected, which is a good thing, the no cover crop baseline, kind of business as usual. The total nitrogen and nitrate that was in the water at the time we collected was about 14 milligrams per liter. Most of that was nitrate. In the cover crop, it was about half. And then in the prairie, it was very low, below 1, as you'd expect. So this is the unfertilized prairie at Cobb's, by the way. There are 2 prairie treatments. There's a fertilized and an unfertilized. So this was great. This was nice to see. We know that we've got management practices that differ in their nutrients. We know that they differ in their, the streams differ in their historical, but also the time we collected their nutrient values. So what we did is we incubated, we mixed the tile water and the stream water together. We incubated at 28 degrees Celsius in a growth chamber with 12-hour light dark cycles. We gently shook and mixed. And before the incubation, we analyzed for chlorophyll A and dissolved oxygen using a DO probe. And then 14 days later in that growth chamber, we pulled the samples out and we analyzed them again for the same thing, for chlorophyll A and dissolved oxygen. And we were looking for the relative difference, or how much each of those combinations of tile water and stream water changed over that 2-week incubation. And this is just a picture of the jars incubating. They're sitting on kind of a raised shelf with the light above head. And you can see some of the jars, and there's a close-up of one jar in particular, had some algae growing. And then when we filtered the water, we can collect and analyze for exactly how much chlorophyll A, which is a measure of algae biomass. And it looks like paraphytic algae growing here in this treatment in B here. Okay, so for all you stats junkies out there, this is an ANOVA table. And again, like I mentioned, we did this twice and we found very similar results, whether we did it in spring or in fall. But what we found is that there are complex interactions with dissolved oxygen, which is one measure of eutrophication, kind of the final step, but only main effects on chlorophyll A. And I'll walk you through that. So there's a 3-way interaction between tile water, stream water, mixing ratio for dissolved oxygen, shown here. So you'd ignore the rest of these interactions and the main effects. But for chlorophyll A, we only found main effects. So I'm going to talk about the main effects of the chlorophyll A first, and then kind of the complex interactions with dissolved oxygen. Okay, so let me walk you through this graph. This is quite a complex graph. Hopefully you can see this. I hope this hasn't been getting in the way. There we go. Yeah, sorry, I didn't realize that. I was looking at my notes slide, but now I see that hopefully that wasn't blocking anything important from the previous slides. So on the top is the chlorophyll A increase. So this is the percent change from T0 to T14, or 2 weeks later. Below, I'm going to unveil that in a moment, the drop in dissolved oxygen. So increasing chlorophyll A is a bad thing, right? So the higher, the worse. The lower the DO drop, the worse, right? It means that there was a large consumption of dissolved oxygen in that 2-week period. And then it's broken up by the mixing ratios, so 5%, 10%, 25%, and then by the stream water, the historical stream nutrient load. So low impacted stream, medium, and high. So as I mentioned with chlorophyll A, it was mostly main effects. One of the main effects we found is that cover crops reduce chlorophyll A by 43%, and prairies reduce chlorophyll A by 46%. So cover crops, this is kind of a really neat finding, is that cover crops are essentially, as far as chlorophyll A is concerned, just as good as reducing algal growth as prairie. That wasn't the case with the nutrient output, but it is with the algae. The other thing we found, so I mentioned how there was a main effect on both from the source of the tile water, but also the streams. So that like we hypothesized, so kind of confirming our hypothesis, the low impacted stream, the more sensitive one here on the left, had greater change in chlorophyll A when was mixed with the tile water. And so that's an indicator it is more sensitive as we expected. Now this is dissolved oxygen. The bars are the same. So the lightest one is the prairie, the middle is a cover crop, and then the darkest one to the left is the no cover crop. And there's a lot of complex interactions here. I'm going to walk you through them. First of all, cover crops and the restored prairie, the RP, reduced the DO drop. So similar to chlorophyll. So that was nice to see. The tile water from under cover crops and restored prairie reduced the drop in DO, or the consumption of DO over that 14 days. Streams with high nutrients, without high nutrients, so the low impacted stream, were also more sensitive to the dissolved oxygen drop. And then the unexpected kind of strange finding is that for dissolved oxygen, the proportion or the ratio we mixed at really had a strong effect. And in fact, the treatment effects reversed at 10%. So at 5%, it matched the algae results. So the business as usual, no cover crop, corn soybean rotation had the lowest or greatest drop or most negative value of dissolved oxygen, but it was reversed in all three of the streams when we mix at a 10% ratio. We're still trying to figure out why this is. It could be something related to stoichiometry or the proportion of nutrients and maybe carbon in the streams. And we're still working on these data to kind of figure that out. Okay, so in conclusion, conservation practices reduce eutrophication, and cover crops is almost equivalent, at least when you look at chlorophyll A as a prairie. It's a little more complex than just more nutrients equals more eutrophication, as that, especially with the drop in dissolved oxygen showed. Mixing ratio is important, so it might be, we showed that even the history of the stream really dictates the eutrophication potential as well. So that's one thing that is more complex than just more nutrients equals more eutrophication. The source of the tile water, prior stream conditions, and that mixing ratio really are throwing a wrench into this kind of simple idea that more nutrients equals more eutrophication in a stream, right? And so as I mentioned, we're kind of trying to delve further into the stoichiometry. We worked with Grace Wilkinson's now at University of Wisconsin. She was IDing some of the algae we found. And so we're looking at a little bit of the algae species that were in our water samples, and looking at that the balance of nutrients with carbon and some other mechanisms that might explain our kind of unusual findings. And at this time, I'd just like to thank again the Iowa Nutrient Research Center, which funded the research. Mrganka carried out all the work. We had some other folks, Teresa Brame, and collaborators like Grace, Michael Thompson, Matt Helmers, Emily and Sam from the Helmers Lab helped us collect the water samples from Cobb's. Steve Potter, Chris Darkin, Haley Wilson, and Morgan Davis all helped with different aspects of the project as well. And at this time, this is a picture of Mrganko and Teresa setting up all those mixtures of stream water and tile water. You can see all the samples they have in front of them. At this time, I'd be happy to take any questions.
Okay, Marshall, while you get ready for questions, and there are some, but folks can type them in. If you can go back to the front slides there about for the information for the CCA credit.
Sure.
We'll go through those couple.
This one, right?
Yep, start with that one. So if you are on here and need a CCA CEU, please send your name, the name you entered to watch the webinar, and your CCA number to Elena Whitaker, ALENAW at iastate.edu. Again, ALENAW at iastate.edu by 5 o'clock today. And then the next slide. If you can. Okay, so we have a new voluntary survey for viewers to fill out. This is voluntary. Only has to be done once. So if you've already done it after watching another webinar, thank you very much. There's a QR code on the screen that you can scan, or I'm putting a link in the chat box that you can go to that. Again, it's voluntary survey for those who participate in USDA funding, which Iowa Learning Farms is in part USDA funded. So for those of you that have filled this out before, thank you very much. And if some more folks can fill it out, that would be great. And then lastly, next slide, if we can. Be sure to tune in next week. Greg Labarge from the Ohio State University, field specialist in agronomic systems, will be talking about quantifying and managing residual soil N after corn. So I think important as we think about the 2023 crop year. Okay, so we did get some questions in here. And the first one, Marshall, is why 14 days? Do you think you might have missed some growth in the first 1 to 3 days?
Yeah, we thought about doing a more kind of sequential growth, but you know, we thought about you know, with kind of expanding like more kind of sacrificial sampling, you have to let go of some things, right? So there's always a trade-off. You saw how many jars were in front of Merganko and Teresa there. And we wanted to err on the side of having some more of the treatment interactions, and then just allowing 14 days because that's usually used for soils. It's also just a good round number. It allows Merganko to kind of recalibrate. So no one's done anything like this to my knowledge. So we were kind of flying in the dark here. So pun intended, I guess, light dark cycles. But yeah, I could see an argument for doing it shorter. I could also see arguments for doing it longer. You know, the retention time of water in some of these pools where, like, especially if the stream is kind of low flow, yeah, you might have, yeah, long. So like, even I could see an argument for even extending it longer than 2 weeks, but.
There was kind of thinking about that with timing and things. There was a question here about that, you know, the presentations about eutrophication in streams, yet the lab study is on bottles where it's, you know, stagnant water. I guess how can you compare the results in bottles versus that water if it had gotten into the stream?
Yeah, we get that question all the time, and I understand that, and I appreciate that criticism. And it, again, I'm going to compare it to soils. We do something called a potential nitrogen mineralization assay. So this is an assay to measure the nitrogen supplying power of a soil, and we bring it to optimum water holding content. We put it at optimum temperature, and so it represents a potential, right? And you know, there are experiments where you could do these kind of artificial streams, or you could even have a, you know, aquatic tank. But again, these are all trade-offs. You would have to drastically reduce your number of samples, your number of treatments. So we chose to go with more samples, more treatments to kind of look at these complex interactions. And we're measuring a potential. Remember, it's a potential. I said that at the beginning. This does not necessarily exactly reflect what's going on in the stream, but it's what would happen under ideal conditions with slowed water, I would say, too.
There's one, I could have asked this question too. What is paraphytic algae?
Yeah, sorry, I used a bit of jargon there. Somebody should have jargon caught me in the middle of that. Yeah, so paraphytic algae is algae that grows on top of usually rocks or sediments.
Okay.
That's different than a phyto or planktonic algae, which is floating in the stream column or in inside the lake in the water column.
Would some of that be what you slip on if you're walking in the rocks that are slimy on the top?
Yep, that's
Okay.
paraphytic
All right.
algae.
Okay. All right. I'll remember that the next time I fall when I'm walking in the stream or lake. Um, so this one, did you look at uh, impacts of tillage as well as cover crop? And I think that's no, because this was a no-till, all a no-till system, and you were looking at the drainage water.
Yeah, it would have been neat. I mean, tillage, and this has been done by Matt, but other folks as well have shown that no-till does reduce nutrient export as well. So, if we had more time and or more funding, it would be neat to do a follow-up study with uh, uh, tile water from a tilled and no-till plots.
So there was another one here. One slide showed organic nitrogen was higher under the cover crop treatment.
Yeah, I think this was these tables.
There was, yeah, the 1.1, but no statistically significant difference. Is that
Yeah, no
correct?
statistical
Okay.
significance.
So there was a question, prairie doesn't need to be tile drained. So is comparing tile output from prairie to cover crops a true control, or is the argument that tile is a proxy for natural subsurface flow?
Yeah, I mean, the way we were thinking about it is just with this kind of three-step, right? That there's management practices that affect nutrient export, and then we really don't know what happens after that, right? You can study all these things in stream that are very difficult to do. You have to have a large sample size or study one stream over several years and change the management practice. But yeah, I mean, there's different ways to think about it. We wanted a gradient of nutrients, and we knew from Matt, your past work and others have shown that non-fertilized prairie has very, very low stream water conditions. So that might be considered a gold standard or benchmark that we could shoot for, even though, like whomever asked that question rightly points out, that a lot of restored prairie doesn't have tile under it. I don't know if there's not any that doesn't, but yeah, that's a consideration. But hopefully that explanation of why we were looking for a kind of a gradient in nutrients that's due to management practice was the biggest thing we were looking for.
Might say it'd be great to collect leachate from a restored prairie without drainage, but the collection of that, trying to collect that may have a big disturbance to the prairie itself.
Yeah, that's a great point. Yeah, another good reason.
But it is definitely a good question. So can you disentangle current N and P in the stream water from historic N and P in the stream?
No, I mean, in fact, the previous N and P were exactly why we selected those streams based on that knowledge. We looked at whether that was, just whether nitrogen or phosphorus content explained and when you mix them, we could kind of sum up the proportion of how much nutrients were in each of those mixtures. That actually didn't explain how much algae growth and drop in dissolved oxygen we got. That was another kind of rather surprising finding. So there's something else going on. Either although the prior management did have an impact, at least on the sensitivity, but when you look at it across all three, the amount of nutrients, the raw amount, just wasn't a good predictor of it, is a better way to put it.
So here's one that maybe could lead, well, we think about additional work maybe sometime, but how would P in surface runoff compare, I guess, between these systems and indicating that some studies suggest, maybe some higher P or dissolved P in cover crop or prairie type treatments. So any thoughts about trying to collect surface runoff samples?
I've never done that before. I've kind of wanted to. I know you've done that, Matt. You and Antonio have done that. I don't know if at Cobb's, but you guys have done it in some other experiments.
Yeah. Yeah, it would be a challenge, but now I'm kind of interested in, could we collect some small plot surface runoff from these areas. Next one is kind of going back to that slide that had the organic nitrogen. This one's on phosphorus, but it said, unless he misread the plot, the P levels in the tile water were extremely low, compared to that. Could you comment on that? I'm tongue-tied now too.
Yeah. No, the phosphorus levels were quite low, and in all, like both the streams and we weren't surprised the tile water was low, but when we collected at least dissolved P was low. I don't have this up here now, but we do have organic or total P, and most of it was dissolved, and what we were able to filter. So we did account for later all the phosphorus that's in there, but at the time we made these tables, that it wasn't included here, but it's still very low.
Yeah, okay, so can you show the one from what it was in the tile water too? Because was it about that?
Yeah.
Oh yeah, not that much. Yeah, and I'm assuming when you collected those samples from the streams, it wasn't necessarily high flow conditions. It was just kind of whatever flow conditions were present at that given time.
Yeah, and we've got that data. We've got the flow conditions, other, the electrical conductivity, pH, DO of the stream water before we started measuring it too.
Right. I don't see two really other questions that maybe Marshall can answer. Again, just in the chat box is the link to the survey if anybody hasn't taken that and willing to take that. Also, if you're on for a CCA CEU, if you can email Elena Whitaker, ALENAW @iastate.edu by 5 o'clock today with your name, the name you entered to watch the webinar, and your CCA number. We'll get that submitted for you. And with that, I want to really thank Marshall for the talk and doing this research. I'll put on my Director of INRC hat. Thanks for doing this research and being willing to talk and present about it. So with that, again, tune in next week. We'll have a presentation from The Ohio State University. So with that, I hope everybody has a great day and week, and we will hope the forecasting of snow is, I don't know, it seems like there's a big wide range of what it might be the next day. So I hope everybody has a great rest of the week.
Bundle up. Thanks for the invite, Matt.